Hello and welcome to this Java tutorial. So in this chapter, we'll explore some of the bitwise operators in Java, which allow direct manipulation of individual bits within integer types, which are byte, short, char, int, and long. So bitwise operators actually have their usage in low level programming, some optimization, cryptography, and scenarios where performance matters. So we'll see some of these uses through examples once we have understanding of these operators. So let's start with the first understanding the operators. So these are the bitwise operators. So we have and. So these are very similar to conditional operators actually, where you have double ampersand and double pipe symbol, at least these two, right? And functionality wise also quite similar, but these operate at bit level. That is the difference. So we have ampersand, that is and, then we have single pipe, which is bitwise or, then we have caret sign, which is bitwise or exclusive or, then tilde sign, which is bitwise complement, then we have left shift, double less than, double greater than for right shift, but that is arithmetic or signed right shift, and then we have triple greater than also, which is unsigned right shift. So we'll see what is the difference between these two. So we'll start one by one. So first is bitwise or operator, which returns 1 if at least one of the operands is 1, otherwise it returns 0. So this will actually work at bit level, right? So if one bit is 1, another is 0 for another number, then it will give as 1, right? For or. Another one, suppose 0 and 0, then it will be 0. So here is a truth table also, which demonstrates the working of or operator. So if this has 0 bit, this another variable, suppose b, that also has a bit as 0 at that particular position, then a or b will be 0. 0, 1 is 1, 1, 0 is 1, 1, 1 is 1. That way it is similar to conditional or. There you have, if one of them is true, then end result is true. Here it is at bit level. So if there is a 1, then it will be a 1. So in 3 scenarios, you will get 1. Then we have bitwise AND operator that will return 1 if and only if both are 1, in this scenario only. Otherwise, it will return 0. So all the other scenarios where one of them is 0, it will return 0 as the end result for A and B. Then we have XOR, which is exclusive or, that returns 1 only if one of them is 1. If both are 0 or 1, then it returns 0. So 0 and 1, then it will return 1. 1 or 0, then it will return 1. Both are 1, then 0. Both are 0, then 0. So that's how XOR works. Then we have complement operator. It is actually a unary operator. That means it will take only one operand, and it is denoted by this tilde sign. What it does is complements. That means it will invert the bit. So if you have a binary number, let's say 1, 1, 0, 0, so it will flip the bits. 1 becomes 0, 0 becomes 1. So that is what you will get as a complement. And there is a formula also. So bitwise complement of any integer n is equal to n plus 1 with negative sign. So if you want a complement of 8, that will be minus 9. Okay, so these are the first 4 operators. Let's see an example where we use these 4 operators and try to understand how these operators work at bit level. Then we will go to the next operators, which are shift operators. So I've already created a class actually to do it. So what we'll do here is we'll take 2 variables. Let's say int x equal to 5, int y equal to 3. Then I'll also write some code so we can see the binary number for these. Then it will be easy for us to understand what is actually happening. So that will get a string. So let's say string x binary equal to. So here we have to use some of the classes and methods. So within string, there is a format method. String class is there in Java. In that, there is a format method. So I want all the 8 digits of the binary. So what I can do is I can do %8s. And what I want to do is I want the binary number. So for every integer data type, there is a corresponding wrapper class. So here we should have a 2 binary string. Yeah. Here I can give x. Then it may have some non-number, right? So I can replace those with 0. This should be character, I think, not string, like this. So if you are not understanding all of this right now, that is okay. But what we are trying to do is for every data type, integer type, so we have byte, long, short, int, there is a corresponding wrapper class. So for int, there is a class also integer, which gives you some method. So there we have a method which converts it into a binary string, this integer. Rest all is to get all the 8 digit, and if there are nothing, then replace them with 0. So we get a proper 8 digit binary. Same thing we can do for y. I'll just do it and show you by running till here what exactly we get. I'll change this to y. Out binary or x plus x binary. Same way, I'll just copy same thing here, binary for y binary. If we run this much, you'll get the binary number for 5 and 3. So if you see, for 5 it is this much, and that is how we get all these zeros also. That is why we have that replace. And for 3, this is the binary. Now let's go to actual binary operators. What we are supposed to do is, let's just print it first. So x and y, x and y, x and y equals this. All right. Then we have 4. So let me copy this thing 3 more times. We have or, we have zor, and for complement we need only 1 with tilde sign. So tilde. With that, if we run it, we get these x and y is 1, x or y is 7, x zor y is 6, complement of y is -4. So that is easy by that formula. So 3, so n plus 1 and negative. So 3 plus 1, 4, negative. But if we have to actually see what is happening, we can do like this. So this is for 5, this is for 3, right? Now, if we are doing AND, what will happen? 1, 1 will be 1. So we'll have only 1. All others will become 0. 1, 0 is 0, 0, 1 is 0. So what will be the end result? This, right? So this in binary is 1 only, 2 to the power 0, this 1 only, right? 2 to the power 0 into 1 will be considered as 1. That is why x and y is 1. Now if we use OR, then these 3 will be 1, right? 1, 1 is 1. This will also be 1. So in case of OR, we'll get this, right? Now, if you see this 2 to the power 0, 2 to the power 1, 2 to the power 2. So 4 plus 2 plus 1. 4 plus 2 plus 1, 7. That is why this is 7. In case of XOR, what will happen? This will be 1, this will be 1. Both 1 will also be 0. So it will be this number, right? So 2 to the power 0, 2 to the power 1, 2 to the power 2. 4 plus 2 plus 0. This will be 0. That is why this is 6. This is anyway 4, but if we go to the actual mathematics, how it is coming to, I mean, actual logic, that is a bit bigger with all the complement and all 2's complement. So I'm not going into that part. We'll go with the simple one, minus n plus 1. All right, so that is how it is doing at the bit level. So bit manipulation. So hope it makes sense. You can check with other numbers also, but that's how you come to the actual result by getting that binary. That is why I did all this. Okay, let me comment this part. Now coming to shift operators. So there is left shift operator which shifts all bits towards the left by the given number of bits. It is denoted by this less than sign 2 times, right? So if you write 2, 2, that means you are shifting the binary of 2 by 2 digits to the left. And whatever is left over, that is filled by 0. Same way with right shift, uh, you are shifting towards the right actually, right, by the given number of bits. So if you have this as right, that means you are shifting 2 digits to the right. So this will do the same thing, but it will shift a 0 into the leftmost position. So vacant position is filled with 0 instead of the sign bit. What it means is when we have a binary representation, right? So most significant bit, which is the last bit, that actually shows the sign. If it is 1, that means a negative number. 0 means a positive number. So it will actually fill with 0 instead of the sign bit. So it will flip that also. So actually, if you see integer, that will have 32 bits, right? So you will have what we have done here. We have taken the last 8 bits only, but actually, if you see, this number will be like this, right? 4 times 0, 0. If you have to do like this, right? That's how it will be. And if this bit is 1, that means it is a negative number. So that is what is telling that instead of the sign bit, it will fill the leftmost position also with 0. So this one also it will fill with 0. That's what you mean by unsigned right shift operator. So let's try to see those also. Let me remove this part, keep it till here. So from here we'll do shift operators. This out. What I'll do is right here itself. If we do 2, left shift 2, right? So actually it will become 8, right? Now if we do right shift 2, we should get it back to the original number. And for that, let's take a negative number. Same if we take minus 8 and triple 2. That will become a big number actually. So if you see, this has become 8, this has become 2, this is a pretty big number. So for that, let me copy this part also here. String 2 binary. 2 binary actually will be 1 0, right? But let's do that also. Binary for 2. and 2 binary. Okay, so binary for 2 is this. Let's copy this also here. Now what exactly is happening when you do left shift? That means you are shifting it by this number by 2. So it will come here, right? 1. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So 2 to the power 3 is 8. That is why it is 8. And this will be right shift. So we'll again shift it here, right? By 2. So we get the same number, right? 2 back. Now for minus 8, actually it will be again, it will take all the numbers in account. It will again become like this. It will actually invert all the bits. So it is again a lot of mathematics to actually do it. So I am not going into all that. If you want to do, then you have to read yourself about two's complement and how it works. Okay. Otherwise, we'll be spending a lot of time in this video itself. And I'll give a link in the detail. There you can go and check. You want, right? You'll get this number for actually this, because all the zeros will become 1 in all the 32 bits. So that is why this big number. So now let's see some practical uses of bitwise operators. So since these operators manipulate individual bits, right? So that is considered fast. So they are often leveraged in scenarios where performance and efficiency matter most. So you will see them used in state and flag management, where you can compress multiple booleans into one integer to save memory. In cryptography also, you can use bitwise OR for encryption decryption algorithms, because that can flip the bits. These are some simple uses. So we'll see that. Fast mathematical optimizations. So multiplying or dividing by powers of 2, that we have seen also, right? When you use left shift and right shift. So you are actually multiplying it by that many digits of 2, power of 2. And you can also use it to find odd or even number. And that will be faster with this, because you are just flipping some bits. So whenever you use left shift or right shift, you are actually multiplying that number by 2 to the power n, right? And when you use right shift, you are dividing it by 2 to the power n. So using these two, left shift and right shift, that we have seen also here, right? Here we are multiplying it 2 with 2 to the power 2. Here we are dividing it with 2 to the power 2. So same thing. Then you can also check odd even numbers. So if you do AND with one of any number, if it is 0, then it will be an even number. If it is 1, then it is an odd number. Why it happens is because every even number, right, that will always end with 0 in binary. You can check that. And odd number always end with 1 in binary. So the least significant bit, which is the rightmost, that will always be 0 with even number and 1 with odd number. So suppose I have this number 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, and 8. This is not there, let's say. Then if you do AND of 1 with that 1, right? So all will be 0. So end result will always be 0. So 1 0 will be 0. All the other will also be 0. So you will end up with 0 0 0 0. So that is the logic which is used actually. So for even numbers, you will always get 0 0 as result. Whereas with odd, you will get 1 as a result, because last will be 1, right? 1 1 will be 1. All the other will be 0. So even means you will get 0, odd means you will get 1. So here itself, let's see. So we did right binary for 2. Let's try with some other numbers. 112, let's say. We'll remove this 2. So 112 binary, if you see, is ending with 0. Any other number. 4, 5, 6, 7, 8. Binary is this, ends with 0. So any even number will always end with 0. And any odd number always ends with 1. 4, 5, 6, 7, 9. Or we take 4, 3, 5. Okay. So that is what is used to find out if it is a odd number or even number. Okay, so let's try to do these as a code also to see multiplication part, division part, and checking odd even in Eclipse. Let's create another class to do these. So bitwise operator usage. Okay, this is the name of the class. That's where first let's see multiplication and division. So this same actually, if we do 2 and 8, right shift. So you'll get 8 for this because you are multiplying it with 2 to the power 2. So 2 to the power 2 it is considered, right? Now if we change it to 3, so 2 to the power 2 into 3, you get 12, right? 2 to the power 2, 4 into 3, 12. And here it will be divided by 2 to the power 2. So 4. 8 divided by 4 is 2. If we change it to something else, then in this case actually you will get 1. Right? Because 2 to the power 3 is also 8. So that is how you can do fast multiplication and division, but it is limited only to 2 to the power of this number. Odd and even. So for that you can quickly do the AND with 1. Let's do it with number taken here. X equal to, let's say, 16, y equal to 17. One is in odd, one is even. Then what we can do is this x ampersand 1. And y ampersand 1. First, let's see. For this you will get 0. For this you will get 1. Right? So for every even number you will always get 0. For every odd number you will always get 1. So you can create a logic using this. If x only 1, right? 0. So using this we can create a logic. What we have to do is this part also in bracket. So if x and 1 equal to 0, then using 1 only we can do both. X is even. From this only we can get the odd also actually, right? So 16 is even. With this only we can check with other numbers now. 17 is odd. 1, 2, 3, 4 is even. 1, 2, 3, 1 is odd, right? So this is working with AND. So I've given you the logic also how it works. Now let's do some coding exercise also. So these are for bitwise operators. So first one we have already done. Actually, check if a number is odd or even using bitwise operator. And if you remember in variable, we did this one, swap or exchange two numbers without using any temporary variable. So this you can also do using bitwise operator. So let's try to do this one. So for that, what you need to do is, first thing we have to do, take two numbers, int a equal to, let's say 7, int b equal to 12. Now we have to swap the values of these two. Actually, that is a property of XOR operator. If you use XOR on two variables and then XOR use XOR again, you will get the other number. So if you use XOR on two variables and then use XOR again, you will get the another number. That is one feature of XOR operator. So what you can do is a equal to a XOR p. Then if you do b equal to a XOR b, a equal to a XOR b. Let's say and b equal to plus b. So is 12 and b is 7. And print here also. So before swap, after swap. A is 7, B is 12. After swap, A is 12, B is 7. Let's say is 57, A is 1, 6, 7, 8, 9, something. Right? So using bitwise operators also. So there are many algorithms actually which are done using bitwise operators. We have done some simple one right now. So this is about bitwise operators and how you can manipulate at bit level, which make it faster to use actually, right? These bitwise operators are fast to use because they do manipulation at bit level, which is faster than using at integer or long level directly. Thanks for watching the video. Please don't forget to like and subscribe.